Thank you very much. It is really a privilege and a pleasure to be here. Thanks for the very kind introduction. I'm looking forward towards a 1 hour of interactive feedback. I'll try not to speak for too long. I'll try to keep this presentation brief. And of course, if you're interested, you can let me know, ask for more, or take a look at the publications. And if there is, I wanted to say, if there is any problem with the audio or with the connection, please do let me know. Please interrupt me and I'll try to fix it. Okay. Also, if there are any questions because I cannot see the chat because I'm sharing my full screen, you can feel free to interrupt as well. So today, as anticipated, I'll talk about integrating terrestrial and non-terrestrial networks. I'll try to give my perspective on this topic and possibly on some research avenues for the future if some of you are currently doing research, PhD or postgrad. So, right. Very briefly about me. So I'm based in Barcelona. My university is called UPF. It's a relatively young university, about 32 years old. But it has been evaluated as one of the top 10 young universities in the world. So we're trying to do very good research. And the topics I'm currently working on are 6G, broadly speaking, and then UAV communications and non-terrestrial networks, which is what I'll be talking about today. We also work on Wi-Fi 8, next generation Wi-Fi. So if you know of anybody who is interested in joining us, periodically we have openings for PhD scholarships or for postdocs. So it's always a good idea to get in touch to explore these opportunities as they come. And yeah, before that, I was working for Nokia Bell Labs and I got my PhD in Australia. This is my email in case you want to interact with me. So let me just say thanks to many of the people I've been privileged to work with in the recent past that in one way or another, they have contributed to some of the results I'll present today. So Adrian from Ericsson, my colleagues from NYU in the States, Angel and Mohammed from my group, David from Huawei, the colleagues from UC Irvine in the States, Himam from Luxembourg, and also the sources of funding. So let's get started. So today I would like to talk about non-terrestrial networks. So the first thing to do is, I guess, be on the same page as to what it means when we talk about non-terrestrial networks. So I try to clarify my view on this in this slide. And I mention explicitly non-terrestrial networks and non-terrestrial users. So what I have put on the left is what I call non-terrestrial networks proper. They're also labeled NTN in the 3GPP work. So this refers to base stations, so cellular base stations, let's say, that are flying in a way. They're not on the ground. So you can imagine a satellite base station. So satellites can be flying at different orbits. They could be in the geostationary orbit, which means that they are at this distance from the Earth, 35,000 plus kilometers. And in that case, from a certain point on the Earth, we see them fixed. We don't see them moving because they're orbiting at the same speed as the Earth is moving, okay? Then we have low Earth orbit satellites, which maybe you've been hearing a lot about, you know, like Elon Musk, Starlink constellation and other constellations, OneWeb, etc. So these are much closer to the Earth. They are between 300 and 1,500 kilometers roughly. But because they're closer to the Earth, they move faster than the Earth. So from a fixed point on the Earth, we see them moving. Okay, this obviously has implications when we want to use them to provide coverage because they are not fixed over there. They'll be moving. Okay, so you need a constellation of these to provide continuous coverage. So as one satellite moves away from your field of view, there'll be another one coming. There's also a lot of research and hype these days on high altitude platform stations, or HAPS. So HAPS are at about 20 kilometers in the stratosphere, as you can see in this diagram. And then UAVs, or drones, if you will, intended as base stations. There has been a lot of work in the last at least 5 years on UAV base stations, optimizing the placement of these UAV base stations to target some new use cases. Typically, let's say they are between 0 and 1 kilometer height, okay? But then what we have on the right is non-terrestrial terminals. So in this case, I'm thinking not about the cells that provide connectivity, but about users that receive connectivity. And these can also be non-terrestrial. In particular, they can be drones. So now you see how you can talk about drones and regard them as base stations, giving you all the flexibility to reposition this and that. But you can also think about a drone that wants to connect to the network, okay? So then in this case, the idea is precisely to consider them as end devices, connect them to the network, and then have the terrestrial network, TN, the terrestrial network support the command and control link to these drones so that they can fly autonomously, and also the traffic that they generate. So the traffic they generate can be imagined similar to our smartphones, okay? Just that maybe there's more uplink traffic than downlink because, for instance, they stream video, okay? But this other type of traffic is new to us, and it's to make sure that a drone doesn't need to have a pilot in visual line of sight. So in a future where we want to have many drones performing many tasks and the whole ecosystem to scale up, obviously it's not sustainable to have one pilot per drone. They will have to fly autonomously. And so if they fly autonomously, the network most likely has to take the burden and the responsibility to provide this reliable command and control link. Okay. Of course, beyond UAVs, you can also have aircrafts or eVTOLs, which stands for electrical vertical takeoff and landing vehicles. You can imagine them as helicopters. So all these new cases that are coming, they can be regarded as users that want to connect to the network. All right, so now if this is clear, let me move on to consider what could be an integration of all these terrestrial and non-terrestrial components from an architectural perspective, okay, particularly for what concerns the radio access. So all the ingredients that I told you in the previous slide, I put them together here into a picture, okay? So what do we have? Again, we have the platforms and we have the terminals. So platforms intended as cells or base stations. We have the legacy terrestrial network base stations, which are typically down tilted. Maybe in the future, we're also going to have dedicated base stations that are up tilted, for example, to serve some aerial users. I'll talk more about this later. We can have satellite base stations. We can have hubs as well, okay? And then we can have different types of terminals, okay? We can have aerial terminals as well as the traditional terrestrial terminals. Their types of receiver can be of different kinds. They could have omnidirectional antennas, for example, in the case of a handheld small device, or they could have some high gain antennas if they can fit a VSAT, which is a very small aperture terminal, something that looks like this, basically, like a small dish, okay? Obviously, this depends on the use case. It depends if the terminal is a car and it has space on the roof, or if it's a mobile phone, or if it's a drone, etc., okay? And in turn, these terminals can relay their access, the signal, to other terminals, okay? And then we talk about UAV relays or UAV to UAV links, etc. Whereas what we call the service links are the links from the user to the cell, no matter whether the cell is a terrestrial cell or it's a non-terrestrial cell, okay? Then we have inter-satellite links, if necessary, or inter-hubs links. And then we have the feeder links that close this loop from the non-terrestrial cell down to a gateway on Earth that connects to the core network, okay? So this basically closes the loop. Why do we need inter-satellite links? Well, if the satellite, for example, is deep in the ocean, it cannot see directly any gateway because the gateway has to be on land, and then maybe you need multiple hops to reach the gateway, okay? So this briefly about the architecture. Now, what use cases can this integrated terrestrial and non-terrestrial architecture enable? Many, I suppose. Here I'm listing only 3 examples, but I'm sure you can come up with other use cases. So the first one I wanted to mention is critical communications. So imagine that the terrestrial network is not working for some reason. There's an emergency, there's a natural disaster. Then all these non-terrestrial platforms can provide an alternative quickly, rapidly, and so they can give more resilience to our network, okay? In that case, you can provide direct access from space, for example, or you can use a UAV radio access node that is backhauled to a satellite. That's the idea. Another use case that could benefit is the one of massive IoT and immersive communications. So what I mean here is that imagine that you want to collect a lot of data from many, many sensors that could be on land or sea. You could use non-terrestrial cells, given their large footprint, because they cover a very large area, okay? And then maybe this could be also used to multicast these signals to many users. for example, for extended reality applications. So satellites are very good on multicasting because multicasting means I send the same data to multiple users because they have a very large footprint, right? So they could be more efficient at that. And another use case I wanted to list here for this 3D integrated network is the one of aerial mobility, for example, urban air mobility. So UAVs delivering goods or even delivering people in the future. The idea is that in Europe, but also many other parts of the world, I'm sure, the majority of the population is going to live in cities very soon, okay? So the idea is to have flying taxis or flying shuttles, for example, from the city center to the airport and back, okay? Or even ambulances, okay? And all of these, at the beginning, could have a pilot on board, but then eventually there will be piloted remotely, and then one day, most likely, they'll be autonomous. So for all of this to happen, we need, once again, very reliable connectivity to the network. And we know that at the moment, cellular networks are in a good position to provide that, but they're not quite ready because they were not designed for it. So now I'm going to expand a little bit on this last bullet, on this last use case, which is the one of aerial services. And I want to bring up this concept of aerial corridors. So why I'm talking about this? An aerial corridor is like a highway, but for UAVs, right? So in the past few years, I've been involved a lot in research for cellular connected UAVs. And what we found out is that it's not easy to guarantee connectivity to UAVs. That's because the networks are designed for the ground and UAVs do not see any obstacles. So there's a lot of interference that they receive from many cells. They also create a lot of interference to the ground. They have mobility management issues, etc. So, but then I realized, together with some other colleagues, that probably the problem is that the task was too ambitious. We wanted to provide connectivity everywhere in the sky, but is this going to be the case? Are UAVs going to be flying everywhere in the future? Probably not. So just like cars, we have many cars in the city, but all of them follow roads, right? You cannot drive a car absolutely wherever you want. It has to be on a road. So the idea is that in the future, we could expect UAVs not to fly wherever they want in an uncontrolled manner, but rather to follow some predetermined routes, okay? So this could be regulated. And then if UAVs will follow routes, then the cellular operator has to make sure that there is coverage on those routes. So this changes a bit the problem for us researchers. We need to rethink the ground network design, the operation, and the optimization of this network, okay? So, and this is going to be what I'll talk about now in the rest of the talk. So basically, I have 3 sections for this talk. I'm not sure we'll have time to cover all of them, but basically, first I want to talk about optimizing the terrestrial network that we have now to cover the sky. Then I will talk about rethinking this terrestrial network by adding more components, again, for the sky. And last, I will think about complementing the terrestrial network with a non-terrestrial network once again for the same purpose. So let's start by maybe re-engineering this terrestrial network for the sky. What's the idea here? This is a work jointly done, ongoing actually, with colleagues from UCI, University of California, Irvine, okay? So we are developing a mathematical framework which is based on quantization theory. I'll skip the mathematical details, but basically this first work wants to optimize the tilts of base station antennas, okay, cellular base stations, to cover not just the ground users, but also some specified corridors in the sky. So imagine you have these corridors where your drones are going to fly. We want to optimize the network to cover both the ground and these corridors, okay? So, and all of this, we want to account for realistic channel modeling and etc. It's a preliminary work, but the results seem promising and interesting because, so when we do this, when we optimize the tilts, so here we have many base stations, okay? This is the base station index. And for each base station, we show the angle. So positive angles means a base station tilted up. Negative angles means a base station tilted down, okay? So there are 3 cases. Basically, these 3 cases in 3 different colors mean that in green, we're optimizing the tilts only for the ground users, which is what we usually do, okay? So you see all the base stations are somehow down tilted. And then in blue, we have when we optimize the tilts only for the UAVs. So in this case, some base stations are actually useless, and some of them are useful for the UAVs, and so they're up tilted, okay? And then in red, we have like a trade-off in the optimization problem that where we use this coefficient 0.5 to trade off the performance on the ground and on the corridors. And in that case, some base stations are down tilted and some are up tilted for the UAVs, okay? So this seems to be an interesting framework. And what we find is really non-obvious because this is the ground area where we have ground users. The dots are the base stations. And this is the resulting cell partitioning after the optimization. So if you've worked on this before, you know that normally this looks like perfect hexagons, right? Hexagonal cells because of the deployment. But this doesn't, because we had to readjust our system parameters to also cover the corridors. Here are the corridors depicted. In this case, there are only 4 corridors, right? And the color means a different base station serving the corridor. So in this case, probably there's one base station, maybe this one, tilted up to cover this in red. Another base station that is covering these 3 in darker color, and maybe a third base station that is covering this. So this is just some preliminary results, but we find the framework very promising. And here is the last plot where I show you the receive signal strength, okay, the resulting receive signal strength, both for ground users and for drones. So what can I find here? I find that for drones, if I don't optimize, then I have this distribution, this CDF of the receive signal strength in green. And instead, if I optimize also for the drones, then I get this red curve. So I boost the performance on the corridors by tilting up some cells optimally. The question is, do I compromise the performance of the ground users? Well, no, because the ground users move from this green curve to this red curve, which is really very close to it. So you're sacrificing a very little performance on the ground, but now you guarantee a very good coverage on the sky. Okay, similar observations can be made for the SINR, but the derivations are more complicated. Okay, so this paper hopefully will be available soon. I don't know if there are questions. If there are, please feel free to interrupt. So now I'll move on to the second part. So before I talked about, I have a network already there. How can I optimize it to also cover the sky? Now the question is, I want to deploy new infrastructure on the ground to cover the sky. So what can I do in that case? Now I'm going to focus on a sub-6 gigahertz scenario. So here's what I have in mind. Imagine that I have 2 operators, okay? One operator is I call it MNOT, Mobile Network Operator T, okay? It's a standard operator, terrestrial, that serves ground users with the standard cells down tilted, okay? But now there's a new operator that comes into the picture, which only wants to serve UAVs. I call this the MNOA for aerial, okay? So this operator wants to serve UAVs, so it deploys some dedicated up-tilted base stations. Now the question is, if these operators share the same spectrum and maybe even the same sites, so for example, through a leasing business agreement, right, where the first operator lets the second operator reuse the spectrum, etc., does it work? Does this pay off? Or is there too much interference between the 2 operators, etc.? So we consider 2 different precoding approaches, okay, the usual 0-4 SIM precoding and some smarter interference suppression precoder to see whether this pays off or not. There will be interference, but is it too much or not? So here I'm showing the SINR in uplink for the UAVs and for the ground users. So the UAVs are here in blue and the ground users are in orange as a function of this intersite distance, ISDA. So what does it mean? It means that this is the intersite distance between the dedicated cells. So when this is infinite, it means I don't have any dedicated cells. I just have the standard down tilted cells. But then as this becomes smaller and smaller, it means I start deploying more of these up-tilted cells more and more densely, okay? 500 meters is when these are as dense as the down-tilted cells, okay? And these are intermediate cases. So just simply, what are the main messages of this figure? So at the beginning, when I start doing this, I start deploying my first up-tilted cells. So the UAVs will be offloaded to these up-tilted cells. The performance gets worse because there's too much interference, okay? However, when I start deploying more and more, the performance becomes even better. Why is that? Because now there are many up-tilted cells. The UAVs will find an up-tilted cell that is very close to them with very good channel. They can also reduce their power because they have very good propagation condition. So they interfere less to the ground users. So in summary, everybody benefits from this in the end, if they're sufficiently densely deployed, okay? So there's an interesting trade-off there. The answer is not obvious. The answer is it depends. And then I talk about two different pre-coding schemes, okay, in terms of signal processing. So this interference suppression always does better because it suppresses some of this interference between the two operators, okay? And if you look at the data rates, then the benefit is much better because now you're reusing the spectrum. So you didn't see this in the SINR that I showed you before, but you see this in capacity. So really densifying the deployment and reusing the same spectrum, the same infrastructure really pays off in terms of rates. In this case, I'm showing the uplink rates for the UAVs. Okay. Now the UAVs have their own dedicated base stations. They don't have to share time frequency resources with the ground users. So that's why the rates are boosted. Now, I was planning to talk maybe very briefly about the same scenario, but at millimeter wave now. Okay, there are some differences. I'll try to go over this quickly. So the idea is very similar. I have an operator, terrestrial one, and then I want to deploy some up-tilted cells. Okay, again, dedicated for UAVs and millimeter wave, right? Why millimeter wave? Well, because there's more band available there. Typically, millimeter wave works well in line of sight when there are no blockages, and UAVs are a very good use case for that because they typically fly high, so they are in line of sight. Okay, and the problem is that there is no clear channel model for UAV communications on millimeter wave. So the millimeter wave channel model from the 3GPP does not account for UAVs. And the UAV channel model, which is from this document, has some specifications for millimeter wave, but it was not calibrated for millimeter wave as far as I am aware. So the first thing we did with our collaborators from NYU was to propose a new channel modeling. So, and we proposed a neural network-based channel modeling with a generative model. So what did we do? We took some data sets from ray tracing. So we took some CTs, okay, and we run ray tracing, we collect data, and then we use this to train a generative model that is able to produce all the channel propagation parameters with the same statistical distribution, okay? And we did this both for the standard down-tilted base stations at the street level and also for some dedicated base stations on the rooftops, okay? So how does this work? Very briefly, this generative model works in two stages. The first stage takes the positions of the user and the base station and predicts the state. So line of sight or no line of sight. And then the second stage, condition on the state, will predict all the path parameters, okay, for each path. The path loss incurred, the delay, the angles of departure, arrival, etc. Okay. So, and here is to show the accuracy of the model. This example is for the City of London. And these plots are for the line of sight probability. And you have the data on the left and the model on the right. And you have the base stations on the ground here, standard, and the dedicated base stations on the rooftop here, okay? So the model works very well. Also, you can see some common sense, draw some common sense conclusion. For example, the higher the UAV, you move up, the higher the line of sight probability, the color gets more like reddish and yellowish, right? Of course. And then these base stations have more blue, it means they're more in no line of sight. Of course, because they are not on the rooftop like these ones. These ones tend to be more in line of sight because they're higher. They don't see as many buildings obstructing them, okay? And so on and so forth. So if you're interested, actually, this is publicly available on GitHub, and we encourage people to use it. And then the same thing with the path flows. You can validate the data and the model for the path flows, and you see some normal phenomena. For example, the dual slope, which is a transition from line of sight to no line of sight, etc. Okay. And then we use this model to actually check, once again, the performance. So is it good to have these dedicated cells? Is there too much interference? Can they help to offload the traffic to them? So we consider this deployment. The standard base station down tilted by 12 degrees, the dedicated base stations on rooftops up tilted by 45 degrees, and then these UAVs that now they have an array because at millimeter wave, you need some directionality to compensate for the attenuation. And this is down tilted 90 degrees. So of course, it's facing down. Okay. The model is the one I talked about before at 28 gigahertz. And what did we observe? Well, we observed that these dedicated base stations, obviously, they see a higher line of sight probability to the drone. And so a better line of sight path and a better antenna gain in general, right? Of course, they're in a better position to serve the UAV. However, notice that many of the standard base stations also have good paths, even if they're not line of sight. Sometimes, through reflection, sometimes they're still able to cover the UAVs pretty well. So it's good news in the end. You could serve the UAVs with standard cells, but if you had dedicated cells, you could do even better. You can offload the UAVs to these. So more quantitatively, this is what happens. So I show you here the percentage of UAVs that are connected to dedicated cells. So the ones in the rooftop. Again, as I deploy more and more cells on the rooftop. So this is the intersite distance. Okay, infinity means there are no cells on the roof, only on the ground. So all the UAVs, no matter their height, these colors mean different height of UAVs. All of them are connecting to the base stations on the ground, of course. But then as I deploy more and more UAVs start connecting to the rooftop cells. And the higher the UAV, the more likely it connects to a rooftop cell. Of course, it makes sense even from geometry, okay? And then with this arrangement, almost all the UAVs find a very good link in line of sight, whether it's with the down tilted cell or the up tilted cell. I'll show you here with these numbers. These are the percentages of line of sight links, and they keep growing. So when I have a lot of up tilted cells and a lot of down tilted cells, no matter where they connect, they pick the strongest, and almost all of them are in line of sight. So the conclusion of this is that these dedicated cells, up tilted, could be used to offload the UAV traffic to these cells, okay? Especially when the UAVs are high. And there's also a benefit in terms of SNR when we do this, okay? So as a function of the UAV height, I show you the SNR in the 5% worst case when there are no dedicated cells and when there are more and more dedicated cells. Of course, this goes up. The UAVs have more degrees of freedom now to pick a dedicated cell in their surroundings, okay? So if you're interested in this, here I'm citing 2 publications where you can find more details. And now I'm going to move on to the last part of my presentation. So far we've talked about the terrestrial network, how to optimize it, how to re-engineer it to serve the sky. But now it's a bit different. Now I'll talk about complementing this terrestrial network with non-terrestrial architecture. So I go back to the beginning when I was talking about non-terrestrial cells, for example, satellites, okay? So I didn't have the time to give enough background about satellite communications, but I hope that the idea will still be clear here. So again, I'm considering a multi-operator setup. I had the usual mobile operator T on the ground, but now the mobile operator T hypothetically partners with a satellite operator, MNOS. And this satellite operator is able to handle some new users, which are the eVTOLs. So imagine you have these electrical vertical takeoff landing vehicles. They fly typically, let's say, at 1,500 meters, okay? Now, instead of serving these directly from the ground network, maybe I offload the traffic to the satellite operator. So is this good? Is there a benefit? So first of all, let me explain why I'm proposing this in the first place. So you probably have heard a lot about these LEO constellations, okay? So the main purpose for launching these LEO constellations is obviously to connect the unconnected. So a large percentage of the world population is currently unconnected. It's a huge problem. I mean, we're talking about around 3 billion people. It absolutely makes sense to launch these constellations to help providing at least basic connectivity services to these communities, right? Maybe in low-income countries or just in areas that are remote where the population doesn't justify deploying infrastructure. So this is clearly the key use case, to connect the unconnected. But because these are deployed in constellations, they will have to move. They cannot be fixed on one point. They cannot stand on the desert or on the ocean, okay? So even in urban areas, periodically, we will have also these satellites. So why not exploiting them to be of some use, even on urban areas? That's the idea. And I think this is really important because how to justify the cost of these constellations is still not clear to the community. Because if you deploy them to connect sparsely populated areas, then by definition, there's not a lot of margin that you can make there. I mean, the market is niche. So maybe it's good to exploit them for different purposes. And here the idea. Okay, so if I had them on top of my urban area, can I offload some traffic and do I get any benefits? So here's what I'll talk about now. There are two important parameters to consider when we look at a satellite base station. Okay, typically they work in a different band compared to the terrestrial network, but there are some choices you can make. So typically a satellite creates several beams on the ground. They are really huge. Okay, let's say 100 kilometers, for example. And these beams could all reuse the same frequency, so the same band, or you could alternate between adjacent beams. There's a trade-off there, because if they all use the same frequency, so this frequency reuse factor is 1, then this is very efficient, but nearby beams interfere to each other. Instead, if you alternate, for example, with a frequency reuse factor 3, then you're losing 2/3 of the band, but you're ensuring that there's no interference. Okay, so it's a trade-off between SINR and spectral efficiency. Another important parameter is the elevation angle. So in this picture, you see the satellite is right on top of the user. This is the ideal situation, 90 degrees elevation angle, okay? But these satellites move. So at some point, the satellite might reach 87, 85, 80 degrees, okay, until a new satellite comes. So this elevation angle obviously depends on how dense the constellation is. The denser the constellation, the more likely that you always have a close satellite close to 90 degrees, okay? And you'll see how these two factors really affect the performance, right? So here's the performance. So we're getting close to the end of the talk. So now I show you the distribution of the SINR for these eVTOLs, okay? There are many curves here. What are they? So the black ones first. The black one is when I have only the terrestrial operator. So the terrestrial operator serves the terrestrial users, but also these eVTOLs, okay? And so the SINRs are not very good. It depends on how many eVTOLs there are to serve. When there are very few, let's say 0.1 per cell, meaning 1 every 10 cells, then you have this performance, which is acceptable. Typically, -5 dB is regarded as outage. Okay, so it's quite good. However, as you start having more and more, as they proliferate, the terrestrial operator cannot cope with them. Many of them go into outage. Here you have 20% in outage. Okay, why is that? Because this massive MIMO framework with zero forcing or even interference suppression that I was mentioning before doesn't work anymore. There's too much interference, and it's impossible to resolve spatially the direction of these because they really are on top of the arrays. Okay, it's basically there is no spatial resolution in that direction. At some point, this breaks. So what happens if I offload them to the satellite mobile operator? Okay, so here I have two cases, in red and in blue. What is the difference? So again, is the frequency reuse factor that I talked about before. One is when all the beams use the same frequency. So because there is interference, the SINR in the red case is lower than in the blue case when I do more conservatively frequency reuse factor 3, right? But you see that in both cases, the SINRs are pretty good, and they're better than the one achieved by the terrestrial network, okay? Of course, this SINR in practice depends on the elevation angle. That's why here I marked some range. When you go from 90, which is ideally the satellite on top of the user, down to 87. You see, there's a degradation, which is really remarkable, by the way. So again, the performance is good, the coverage is good, but it also depends on the frequency reuse factor and the elevation angle. So how dense the constellation is, etc. And of course, these translate, this is the SINR, it translates into rates, which I'm not showing for the sake of time. We made these calculations accounting for a certain area, certain population of the eVTOLs. The performance really depends on how many you have. So if you have too many, then too many are in outage, too many need to be offloaded to the satellite, and then they have to split the time frequency resources. So their rates are pretty low. However, if you have very few, then very few are in outage. And these very few can be multiplexed more efficiently by the satellite. That's why the rate is at least one order of magnitude higher. Okay. So more details can be found in this paper that was just accepted in IEEE Communications magazine. The title is the same title as my presentation. All right, so to conclude, let me point you to some references. So the first two are the papers most related to this talk. It's my last two papers, the one I just mentioned and this tutorial paper on UAV communications. But also I wanted to list some other very recent references for the last 2 years on these topics that I recommend taking a look at. And so to summarize, what is the vision? Well, what I wanted to convey to you is that this new 3D network brings a lot of opportunities and challenges. It brings opportunities because, first of all, it could be that we finally managed to connect the unconnected world. So this will open new markets, obviously, but also to hyper-connect the already connected, for instance, by being able finally to support new services and new applications and new use cases. Today, I focus on the aerial ones, but there are more, obviously. From the research perspective, this is also challenging and therefore exciting, because a network like this has a very heterogeneous architecture, different types of services with different requirements, and different spectrum and frequency bands with very different behaviors and features. The capabilities of the devices are so diverse. You know, we have smartphones, IoT sensors, big drones and small drones, and so on and so forth. And also the type of cells, okay? Satellite cells with a huge footprint, but a lot of propagation and delay, terrestrial cells, hubs, and so on and so forth. The ownership is a very important factor because there are new players that come into the ecosystem. Who owns the satellites, who owns the spectrum, the mobile operators, the vendors, etc. And so what we need is a unified optimization of these deployments and the operations, how to deploy and how to run this 3D network. I'll try to give a few answers today, probably a lot of questions, right? So I'm excited, and I think this is a good research topic, and so I would like to be part of this in the next few years. And if some of you are also interested, then I would welcome any feedback or any collaborations. Thanks very much.
Thank you, sir. Thank you for your wonderful presentation. Participants, do you have any questions? You can unmute yourself and you can ask question directly. No need to use the chat box. Have any specific questions to sir? You can unmute yourself. Sir, I have one question.
Yes, please.
Why is there any specific reason to choose 28 ZRs for this UAV applications? 28 gigahertz
Right.
millimeter wave.
It's because, as far as I'm aware, this is one of the bands being allocated in the United States. So out of all the millimeter wave spectrum, some bands are better than others because of the attenuation and the absorption. All these phenomena, right? They happen at certain frequencies. So some frequencies are better than others. Out of the available frequencies, I'm aware of the 28 gigahertz band and of the 60 gigahertz band. So we focus on the 28 gigahertz band now. Of course, the study can be repeated at a different frequency. You just have to collect some, for example, ray tracing data at 60 gigahertz, train the neural network with this new data, and hopefully then it will work.
This is going to be the reference band of millimeter wave, the initial band, like that, sir. 28 gigahertz.
I think it depends on the country. It depends on the country. Different countries are allocating different millimeter wave bands for 5G new radio. So I think this is country specific. But 28 gigahertz, as far as I'm aware, is one of the most broadly used.
But for India, we talk about only 700 megahertz and 5 gigahertz and some bands of 5 gigahertz and 3.7 gigahertz like that for 5G use cases.
Yeah, but those are not millimeter wave. Those are not millimeter wave bands.
Yeah.
So those are, yeah, the subscale. So that means that maybe they haven't allocated a millimeter wave band yet. Even in Europe, there are not many millimeter wave deployments, but this will come with the rollout.
Okay, sir. So it depends on the country, the millimeter wave band. What about 60 gigahertz, sir? 60 gigahertz millimeter wave. 60 and
well,
70,
the framework,
yeah, that
the
higher bandwidth
still applies. Yeah. Sorry, I think my connection is a bit choppy. So yeah, the framework still applies. In terms of research, everything is very similar. It's just the parameters of the channel are different. Maybe you have more attenuation, so you have more path loss. Maybe you need to make your cells smaller because you cannot reach very far, or you need arrays that have more elements, so they are more directive, so they can compensate for this attenuation. But in terms of research, this is very similar. It doesn't change that much.
Okay, sir. Thank you. Participants, you can fill up the feedback form so that I can share with the professor in future your feedback about this session. You can fill up the feedback form. Any other questions? Any other questions? And this is the 3D opportunities are actually we are working always with 2D, and this is a new dimension professor has explored, and so definitely you should have some idea. I think, sir, Vijayendra Babu sir.
Yes.
Sir, are you there?
Yes. Can you hear me?
Yes,
Hello?
sir. Yes, sir.
Yeah.
Sir, kindly remove your screen sharing option, sir. I would like to share e-moment for you. Yes, yes. Sir, kindly accept this e-memento as a token of our gratitude and our love. Yes, sir. Is it visible?
It is. Thank you very much. This is really nice of you. Thank you.
Thank you, sir. I will send it through mail, sir. Thank you. Thank you for accepting our invitation and shared your experience with us today. It's very useful. And many are working in this wireless domain. So whenever we put a invitation about any wireless topic, many of them are very much interested. So and your topic is very, very interesting one. And the emerging ones. Thank you, sir. Thank you very much for joining with us.
Thank you. My pleasure, really.
Yes, sir. Thank you.